This recording is about energy, specifically free energy. Why does it exist? Why is it not a fantasy? Now, normally I don't like physicists. I don't like what they do to the practice of electrical engineering, but I'm going to have to make an exception now because I have to use their relativity theory to explain where free energy comes from. Now, we all probably are familiar with the example they offer us, the only example they offer us in how we can manipulate our world. And that is the example of a pair of twins, and one is sent in a rocket ship, a fantasy rocket ship, to travel at either the speed of light or nearly the speed of light. And they both have watches on. And so one takes off and the other one stays behind. And then after 70 years, assuming the brother is still alive, the other one comes back and returns. And he never stopped. He was in constant motion during that entire time. And we compare their age and we compare their watches. And lo and behold, the person who traveled at nearly the speed of light did not age perceptibly, and his watch only advanced a microsecond or something, a very short period of time. Meanwhile, his brother, who stayed behind, aged considerably and probably died, and if we kept his watch, and if his watch is still running, it would show that 70 years have passed. From his point of view, while his brother, who was in transit the whole time at the speed of light, did not age at all. Now, this is a nice little fantasy, and it actually explains, it doesn't explain, but it serves as a jumping point from which we need to fantasize further in order to explain how is it that free energy can be true and not violate any laws of physics. It's because of this. It's because of relativity, of all things. I never thought I'd come to this to actually endorse the physicists' relativity, but there is really no other way to bridge the gulf that exists between us, those who are protagonists in support of free energy and those who are antagonists who are against it, and still satisfy the criteria of physics and satisfy the simulator, which has been teaching me, training me for the past 6 years intensely, because I spent a lot of time at it, especially in the beginning, the first few years, especially the first year, training me on how to think and be brainwashed by the simulator rather than by conventional wisdom that free energy does indeed exist. But how do you explain it? The simulator doesn't know. All the simulator knows are mathematical equations. In fact, it doesn't even know what time is. To the simulator, time is just a number, and it figures into its calculations, but it doesn't know what time is. It doesn't know what capacitance is or inductance. Only we know that. So I have had to make available to myself, make use of, whoever had an opinion that might come close to explaining the situation, but none was really satisfying, especially to the antagonists, who keep saying, no, you're violating the laws of physics, you're fantasizing, you're being sold a bridge, or a piece of real estate for an ungodly price, you need to go back to school. I never went to school in the first place, that's why I'm able to think this way. So here it is, my version, according to Vinny, of how physics explains free energy. All right, you ready? You got your seatbelt firmly tied, tying you down so you don't jump up out of your seat? All right, here it is. Now, I just explained to you the idea of two twins. So I'm going to start with that, because there is a generic factor or ingredient to what I'm going to explain, and it's time. Although for the purposes of discussion, I will have to correct myself and use the term duration in place of time, because it still involves the concept of time, but it's more specific and accurate as to how I'm going to use time to explain free energy in terms of physics, in terms of the relativity of physics. So duration is a factor to consider, a very important one, because let me give you another example to demonstrate how important duration is. We want to talk about a car that we want to increase or decrease its speed, but specifically let's just choose one. We want to increase its speed, and we know it's going to take extra energy from the motor to accomplish that. Let's assume it's an electric motor. This is an electric car. Now let's also assume ideal conditions to make everything easy on ourselves, so there's no friction, there's no wind resistance, there's no inductive impedance. So we're cruising along at 40 miles an hour, and we're not spending any energy to maintain our momentum because we already spent the energy to get up to speed. But now we want to speed up, and we want to pass this big, huge 18-wheeler that we've come upon that's right in front of us. He doesn't want to budge or move into the lane to the right. And so we want to pass him on his left and or her, in case it's a her driving. And we want to accelerate, so that means we're going to draw more energy from our battery pack in order to accelerate to 50 miles an hour in order to pass and get ahead of him, and then we can decelerate, or we'll keep it simple. We'll just stay in that lane that we moved over to the left of him and keep going at 50. So we're no longer going to go at 40 miles an hour. Now we got to have more energy to accelerate. And that acceleration is called speed. And we measure speed in terms of miles per hour. Now, according to the relativists, traveling along at 40 miles per hour at a constant speed, we don't notice it because the car is not accelerating, so we don't feel that push against our body, pushing our body back into our seat, that G-force, that force of acceleration that pushes us back into our seat, especially if we do it suddenly like I like to do and floor it. I want immediate results. Well, if we're cruising at 40, we don't feel that. It's kind of like free fall, parachute jumping free fall. You think you're weightless. If you're inside the passenger area of a plane, all the seats were taken out because they're for skydivers practicing. So they do a dive, but they dive at the correct rate so that you're now hovering in the middle of the craft there, demonstrating or feeling what it's like to undergo free fall. You don't feel any gravity. You don't feel anything. You're just floating around inside the craft. And that's kind of like what you're doing when you're driving at 40 miles per hour at a constant speed on the freeway, and it's straight, so you're not making any turns. You don't feel your body pushed against your seat or thrown to the left or thrown to the right. You feel, for all intents and purposes, if you were asleep, you'd remain asleep because you would think you're still parked in front of your house. It's only when you speed up, in this case, we're keeping things simple, that you feel something, your body feels something. That's acceleration. That's speed. That's something we can measure just by our body. You put a spring behind you, and you could measure speed based on how much force was applied by your body against the spring to register, oh, you're now traveling at 10 miles per hour because you are traveling 10 miles per hour faster than the 40 miles per hour that you were cruising at, because now you're doing a total of 50. Your speedometer on your car is telling you 50, but the G-forces, if you've got another separate meter measuring your G-force of your body, now it's telling you 10 miles per hour because that's the additional speed you're accelerating to pass that 18-wheeler. Well, that accelerative force that registers that extra speed of 10 miles per hour, how do we measure that? We don't say a singular measurement, we say miles per hour. Now, hour, time, is a factor of reactance. It's a generic factor that pertains both to magnetic reactance as well as electrical reactance. Now, I have to admit stupidity, or ignorance, I should say, my ignorance on the topic of magnetic reactance, because I've never studied it. In fact, only recently did I bump into its existence. So I didn't even know it existed. All this time for the past 6 years, I've been studying electrical reactance, the factors of electrical reactance, because that's what Eric Dollard presented to me, and then I looked up online the equivalency terms in terms of electrical reactance terminology to what he was saying. He was saying that if you want to synthesize electricity, he's very careful. He doesn't want to say create energy or manifest energy, since that violates the laws of physics. So he used the term synthesis. Okay, so in order to synthesize electricity, it's like ingredients of making apple pie. You need the wheat flour and the sugar and, the eggs or whatever, the butter, to make your apple pie. Otherwise, you can't make apple pie. And so it's like that with electricity. You've got the conventional term, the electric field, although he prefers to call it the dielectric field. You could call it the electrostatic field if you prefer. And then you have the magnetic field, and you also have time. And with those three ingredients, the dielectric, the magnetic, and time, he says, you can make electricity from those three ingredients. You can make your apple pie. And you can also disassemble it if you prefer. And I found under simulation, if you take the phase of current and the phase of voltage and separate them by 180 degrees of temporal separation in time, that you can do whatever you like. You can play God. You can make energy disappear. You can make energy appear, seemingly out of nowhere or into nowhere. And it's the seemingly part and the nowhere part that the purpose of this recording is going to explain to you what my latest insight is that I think solves the riddle. Okay, but getting back to Eric Dollard. So we got these three ingredients, and they come out of electrical reactance. Now, one of them is generic to reactance in general and is not specific to electrical reactance, and that's time, or what I prefer to call duration for the purposes of putting my attention on the subject. It's going to be duration. In other words, when I sometimes when I am designing an over-unity circuit under simulation, and I'm not very good at it, I don't know what I'm doing, and I have a long ways to go yet still before I get to the point of polishing the polish. But this is more like really not fine-tuning anything. It's more like big, I want to get over unity, and how do I do it? Well, I don't know, but I'm sloppy, and so I have to, if I'm patient, and if I run the simulator, and if I can get away with it without the simulator giving me error messages and freezing up on me early on, but if I can run it for 10 million seconds in simulator according to its version of real time, which of course is not, it's all digital, it's fake, it's fantasy, but according to its frame of reference, its relativistic frame of reference, it counts out 10 million seconds and gives me the results. If I see over unity, if I wait long enough, then at least I know I've got something. I just have to improve efficiency to the point that it can deliver the same results in nanoseconds. And I usually can, because I know what to deal with. I play with the other factors that Eric Dollard has taught me. I have capacitance, which modifies the electric field, which he likes to call the dielectric field, which you can also call the electrostatic field if you prefer. And then we have inductance, which manipulates the magnetic field, which has an impact on current and amperes. And there's another one that he didn't mention, but I already mentioned it. It's the phase relation between current and voltage. And I have to use that first in order to be able to manipulate capacitance and a capacitive reactance and inductive reactance separately, or else they're still going to be glued together as electricity, and I won't be able to manipulate them separately. Because I have to be able to manipulate frequency is another one that Eric, well, he says time, which kind of covers a lot of things. So time covers the generic aspect of time, namely duration, but then it also covers frequency, which is specific to electrical reactance. Now, whether or not it has an analog over in magnetic reactance, I don't know, because I am ignorant on magnetic reactance, subtopic of reactance in general, reactive power in general. But I do know in the field of electrical reactance there's something called frequency. So I have to set up the precondition of separating current from voltage by 180 degrees, by a whole half cycle of oscillation of temporal separation, in order to be able to manipulate these other three factors in whatever way I like, separate from each other, to get the results I want, because I'm going to have to. Now, I'll also have to wait, but ideally I want a circuit, and I have managed to do this, but only on a few occasions, so that I can get it so fine-tuned that I don't have to wait more. I can wait specifically 100 milliseconds or thereabouts, give or take a couple hundred, because if I'm trying to supply over unity, free energy to an electric vehicle, I want a response time in 1/10 of a second, because if I want to pass that 18-wheeler, I don't want to have to wait a second. Now, I have to tell you, this Ford Fiesta that I tootle around in, they actually put a delay in there, so I can floor the gas pedal, yet I have to wait a whole second before I even begin to hear the engine increase its speed. And then I have to wait additional amount of time for that increase of rotation of the motor to give me the lunge forward that I need to accelerate, and now I have to wait for the acceleration to transpire and give me the extra 10 miles per hour. So I have to wait an additional amount of time, all because they put a delay on that accelerator pedal. It's bad enough, when you're dealing with a small car, it takes longer to accelerate usually, unless you're given a race car engine, which mine does not possess. But they put an extra delay on because they don't want you to accelerate suddenly for some god-awful reason. It took me forever to get used to it because I was furious when but I had no choice. I'm kind of stuck with the car. Be that as it may. So we have, ideally, I would like a response in 1/10 of a second. So that's one factor, is your response time. But to do that, you have frequency to play with, you have capacitive reactance coming out of capacitance, and you have inductive reactance coming out of inductance. Three different ingredients to manipulate after you already have separated your current phase from your voltage phase by 180 degrees to be able to do these separate transformations without one being tied to the other, so that you can get exactly the results you want. Now, that's ideally, under ideal conditions, what you want to do in a free energy circuit. But see, I can see now why I had problems sometimes. I don't always get that latitude, the luxury of that latitude, because I did not pay attention to magnetic reactance because I was ignorant that it even existed. So now that I know better, now I know I need to study magnetic reactance. And I don't know if the simulator is going to give me those options or not. I'll have to find out. Anyway, assuming that we have an ideal situation in which we don't have to worry about magnetic reactance, we can just manipulate electrical reactance for the purposes of this discussion. Those are the factors I deal with and the reasons why I deal with them, because they will give me what I want, assuming, barring any complications, which usually happens most of the time, such that I have to get into magnetic reactance, which I haven't been doing so, and so it's no small wonder that I have difficulties more often than not getting precisely what I want, the result that I want. Because a motor controller, it doesn't want you to give it random series of amperage and voltage. It wants a constant supply of power so that it can then manipulate that according to the demands that are made by the motor under specific conditions, such as acceleration or going down a hill or whatever. So I started out by talking about miles per hour because everybody knows about that. Now, what I did in that example was very overly simplified to what actually happens in real life. When they teach electrical engineering, they keep it simple, and they keep it simple even when they send the technician out in the field, because they don't want you to know about free energy. So I'm giving you something your teacher did not give you, and you won't find it necessarily in the electrical engineering books. So I'm going to try instead to avail myself of real-life examples that you can relate to, and I've already given you one. It's miles per hour. But let's explain that. Let's go over that and see how it relates to explaining where free energy comes from, or beginning to explain where free energy comes from. Miles per hour. Miles is something tangible. We know. We can pace out a whole mile. Pace it out and you know, measure each pace. Okay, so maybe I have a meter length to each one of my paces, and so I pace it out, how many meters in a mile, and oh, I got it now. It's something physical. I know it, but time is not. Time is a fantasy. Time is a mental construct. It's a man-made way of dealing with something which is not tangible. It's intangible. And this is what I'm going to try to convey to you, the idea of how intangible is our measurement of energy. Because we take something physical, in this case miles, and we measure it in terms of something that is not physical, that's merely a man-made construct we call time, but in this case, hours. Miles per hour. And this takes us back to what I started out by talking about. I'm going to be explaining, justifying, I'm going to be proving where free energy comes from. It comes from the physicist's idea of relativity, in which your frame of reference means everything when it comes to drawing conclusions about your reality. So that if you're traveling in the spaceship at the speed of light, you're not going to have the same reality as the person you left behind who is not traveling at the speed of light. So relative to the brother who's now traveling at the speed of light, the brother left behind is not traveling at the speed of light by comparison. You know, he's traveling at a different speed, but then you both were anyway in orbit around the sun, standing on the surface of planet Earth. But we're going to ignore that because you were both traveling at that same orbital speed around the sun, so we're not going to worry about that. Plus, it's a different trajectory as opposed to the spaceship going off in a straight line or some other direction away outside the orbit that the Earth takes around the sun. So, you know, that's an extra complication. We're not going to worry about it. But in any case, just thinking about speed alone and how we measure speed, we take something tangible, miles, that we can physically pace it out, walk it, we know it exists, but we measure it in terms of hours, which cannot be held in the palm of your hand. And in fact, you don't even know what it looks like, tastes like, feels like, smells like, or sounds like, because none of your five senses are going to help you. It's simply a concept. And in fact, I'll give you a little clue here. Relativity has everything to do with it, because when you've got an oscillating circuit, from the point of view of that circuit, its time frame is that oscillation. Our time frame are the hands on the clock or the digital numbers on our digital watch. That's our frame of reference for time. But when you've got something oscillating, let's say 60 cycles per second, the AC grid, that's its reference for time. Not ours. Its reference is that oscillation of energy that is giving it 60 cycles per second. That's its reference frame for time. So time is relativistic according to the observer, whatever you are oscillating at. And there was an episode on the original Star Trek TV episode, you know, back in the 60s, in which they covered this theme, in which they had somebody come on board, and they didn't notice it at first. And after a while, they began to notice this. They began to become suspicious. We seem to have brought somebody on board, but we can't find them. And they look all over the ship, and they can't find them. They're not, you know, but they really are now convinced they're stowaways on board. When they beamed up from the planet they were visiting, somebody else came along for the ride, and they don't know who it is or where they're hiding. Well, they realize they're not hiding in space, they're hiding in time. Because they're vibrating at such a fast pace that they're zipping around and doing things like 100 or 1,000 times faster. Everything they do is that much times faster, and so they don't realize that they're there. And from the aliens' point of view who came on board, The Star Trek crew are statues standing still in frozen position, not doing anything. Well, they are. It's just so slow you can't notice it from their point of view, the aliens' point of view. But from the Star Trek crew's point of view, they don't even see the aliens, let alone maybe a flash of light passing by them or a breeze of air. Nothing. They're so fast they don't even notice they're there. So this is important because when you change your reference of time, everything else, it affects everything else. And so that's why we measure acceleration due to the extra energy we're spending to add 10 miles per hour to the 40 that we're already doing, that we're already cruising along at. That extra speed is giving us, that extra energy is giving us the additional 10 miles per hour that we measure in terms of hours. That extra 10 miles of acceleration we measure in terms of hours. We measure the tangible in terms of the intangible. We measure the real in terms of the non-real. And this is applicable to energy. When we make the claim, oh, energy in has to equal energy out. Because the circuit's going to perform a little magic trick inside of itself. It's going to change its perception of energy per units of reactance. Now, reactance is predicated on something extremely non-tangible. It's called the square root of -1. And purely reactive power can be renamed imaginary power, because it's not complex anymore. It's not real plus imaginary. It's now purely imaginary. It's purely the square root of -1 times some value, which is still predicated on the square root of -1. And the square root of -1 was invented by, Hipparchus or somebody, some ancient Greek dude, a couple thousand years ago. But it wasn't until recently, namely a couple centuries ago, that a philosopher by the name, or maybe he was a mathematician by training as well. I knew him, I learned about him in high school, that he was a philosopher, but he might have been a mathematician as well. And by the name of Descartes, a French dude. And he pinned the name of imaginary to that type of number that is the square root of -1. Why? Because he was pinning that name out of derision. He was trying to, poke fun at it, that it's imaginary, that it's not real, that it's just a fiction. Yet all of electrical reactance is predicated on that fiction, in which real power disappears because it turned into reactive power that you can't see anymore, because it's the square root of -1 behind it, to a certain degree, depending on to what degree that is the case. And in this case, I'm trying to be extreme about it, so let's just say it goes 100% into the reactive realm. Now you don't see it. It literally disappeared into nowhere. And yet, due to the fact that Descartes pinned that term, semi-making it practical, okay, now we can use it because we got a word to describe it. Now, to encourage people to use it, now we can perform mathematical computation and say, see, this is how much energy disappeared or converted, but disappeared for all practical purposes from the real world of real power into the imaginary world of reactive power. And it should, if it all came back, converted all the way back, it should all come back as real power. And sure enough, it does. And so we polish our knuckles on our chest and we say, what a smart boy or girl I am, because the math worked to justify the experience that transpired. So, more or less, obviously it never does entirely so. There's always some discrepancy. But the math works because the theory behind electrodynamics has been around for over a century. So we have all this testimonial and working knowledge. We have a lot of mileage behind us, so our equations work most of the time to a large degree. Yet we can't prove it, because it all disappeared into the imaginary world, which Eric Dollard prefers to call counterspace. Be that as it may. So, miles in terms of hours, something tangible in something in terms measured in terms of something that is not tangible. Something real is perceived in terms of the non-real. In other words, when we measure energy, we don't say kilowatts. We have to get joules. But what's a joule? It's the wattage in terms of time. In other words, it's kilowatt hours when we get our electric bill. And that hour is pretty fictional because you can't hold it in you can't prove that time exists. Yet we do it anyway. We measure everything in terms of time, energy in terms of time. Kilowatts spent or that we used in terms of time, an hour, and then we get billed for it and we pay our bill. Or we don't pay our bill and our power gets shut off. So it must be pretty important if our power gets shut off that we pay attention to the hours that we spent those kilowatts within that duration. So this is how to look at free energy. There's no other way to do it. But I left out something that I didn't get to yet. So far so good. I've covered all the bases in terms of what's already conventionally known. So I haven't given you any new information. I've just covered all the bases that we already know before I get into the area that we don't normally think about, that we do know about, but we never bother to connect the dots to draw the conclusions that would totally justify and explain free energy in terms of already pre-existent conventional wisdom. No need to come up with a new law of physics or a new law of thermodynamics or whatever to explain free energy, and no need to explain it out of existence claiming that physics denies it. No, it does explain it, and it's relativity of all things. The very thing that so many of us free energy buffs poo-poo, the very thing will explain free energy, and this is how it's done. Time is a generic factor or ingredient of electrical reactance, of reactive power, of impedance. All the impedances that are specific to electrical reactance, electrical reactance is part and parcel, is an ingredient to the generic framework of reactance, which is only one factor, the generic factor of time, which I prefer to call duration. Not frequency, because that's something else. That's a specific subtext to electrical reactance. But the generic context is time, duration. The generic context of time is duration. And that is a factor of reactance. That comes straight out of the more generic subject of relativity. So reactance is a subtext to relativity. I hate to admit it, but it's the fact of the matter. I have to admit it publicly, that I have to agree with the physicist, but they have to agree with me. It goes both ways. It doesn't go just one way. I'm willing to concede, but are you, physicists, willing to concede as well? That's the kicker. Because once you concede that duration is the generic aspect of time that explains reactance, explains the relativistic point of view in which we measure something physical, miles, in terms of something non-tangible fantasy called hours, in order to justify our measurement of the acceleration, the amount of energy we spent to accelerate 10 additional miles per hour on top of the 40 that we were already cruising at, we have to accept the fact that we're dealing with reactance. We're dealing with relativity at the same time. Well, if we do that, now we have to take the next step and concede that if we're willing to do that generically over reactance in general, we have to concede specifically as well. We have to include capacitance. We have to include inductance and their consequential capacitive reactance and inductive reactance and the forces that create those consequences. What are they called? It's not called capacitive impedance. What's it called? No, it can't be. The dielectric, I guess. The dielectric impedance. I don't know. I'll have to say dielectric impedance. And then there's the magnetic, the inductive impedance. So it is capacitive impedance. That sounds funny. I'd rather call it dielectric impedance. Anyway, those two impedances, and then you got frequency, and then, of course, you had to do phase relation shifting in the first place in order to manipulate those three other factors. So those are aspects of relativity, because they are aspects of electrical reactance, which is a subtext to reactance in general, which time is already a part of, which is already a part of relativity. So you see, I'm connecting the dots. I didn't come up with anything new, but I came up with conclusions that are new from the standpoint of conventional wisdom, which ain't so wise because it doesn't think of all these conclusions that it should have come to all along and admitted to people. But see, it takes people to do that. Scripture is dead scripture until it becomes a living embodiment within the mind, body, and life and feelings and perceptions, most importantly, the perspective of the individual. Otherwise, it's dead scripture. Otherwise, it's a fantasy that we argue over, claim to be, by the naysayers who say, well, you're fantasizing, you're selling a bridge, and I don't want to buy it. And you're a con artist and not very good at it. I've had all kinds of things told about me. Oh, you're stupid or ignorant and you need to go back to school. Nonsense. I learned this on my own from the simulator and from teachers such as Eric Dollard, but not entirely, because now I have to figure it out on my own. How do I bridge the gulf between us so we stop arguing? Because it's silly to argue. Electrical engineers have had this knowledge for over a century, but they have never connected all the dots as a acceptable collective opinion. There have been individuals like Eric Dollard. He's formally trained. He's an electrical engineer. There's Jim Murray, who was formally trained initially as a physicist, and then he decided to become an electrical engineer because it pays better. Okay, whatever. Then there's Paul Babcock, who did things a lot on his own, but he was formally trained, but he also had a lot of streetwise experimentation in the lab, just monkeying around, trying this, try that. You know, there's all kinds of approaches to the learning process, but regardless, when it all comes down to how do we talk about it, what kind of concepts, theories, and terminology, it turns out relativity explains free energy. It explains why Gabriel Cron could boast, give me any circuit, pick any two junctions, any two nodes within that circuit, and then tell me what you want me to do and how much. Do you want me to make energy disappear? Do you want me to make energy appear, and how much in either case? Just pick one of each, so narrow it down, and then I will make it happen. I will connect to those two nodes. I will make a specific amount of energy appear exactly the way you tell me to do it. That's how good the guy was. But all of his knowledge was proprietary, owned by the company that he worked for, under which he learned all this stuff. So they owned all the knowledge, and he couldn't share it to us share that knowledge with us, except I'm sure he did generically in a very broad way, because he authored two huge books. They're like telephone books. They're so huge. If you're old enough to know what a telephone book is from the old days, and telephone booths, we had them dangling inside the telephone booth, and they were pretty big. They're like your Bible. They were the size of a Bible. But he authored two of these Bible-sized books on the topic that was behind his skill. I haven't bothered to read the books, and I knew that there must be a shortcut, and there is. 6 years of intense self-study on various simulators, and then going any which way I could to try to find theory. I went to the optical engineers, and I learned about phase conjugation, but, that's who uses that terminology and concepts in real life? Nobody does. So, okay, I need something I can sink my common sense into. The common sense I was programmed as a child that we all possess. And then I can explain it to the next person beside myself in a way that whether or not you accept it, that's your business. But at least I didn't have to reinvent the English language to do it. Not too much. I had to use a little electrical engineering terms, but most importantly, I used real-life examples that we can all relate to. That's important. Otherwise, there's no point to discuss the topic if you can't bring it back down to earth to common experience, common sense that everybody understands in today's world. You're sitting in a car, you're driving, you're accelerating, you want to pass the dude in front of you. What happens? We all know what happens. So if I can't explain it in terms that we can all appreciate, then I don't belong doing what I'm doing. But I set myself the task because I felt I was up to it, and it turns out, with a lot of patience and hard work, I got to this point that I can make this recording and explain it in the very terms I never dreamed I would do, in terms of relativity. But you know what? It works. It fits the bill. It explains it. And it satisfies all the criteria of electrical reactance and generic reactance. It satisfies why the simulator will see the nanowatt or picowatt of either microvolts or microamps that I'm feeding it. Yet if I wait long enough, either nanoseconds or 10 million seconds or anywhere in between, its perception of that nanowatt or picowatt will change over that duration of time to the point that now it's spitting out 100 kilowatts of energy. 360 volts versus 200 amps. I mean, it's ridiculous. Well, not 100,000, more like 67,000 watts, but still, about 100,000 watts. I mean, it's ridiculous. Where did the simulator get the idea that all this energy just came out of nowhere? Well, it's a round-off error due to the floating point decimal system that the simulator utilizes. You know what? You know how far that argument goes? Not very far. You know why? Because I switched over to 64-bit Windows 10 operating system. And when I reinstalled the MicroCap 12 from Spectrum Soft, I no longer had to use their 32-bit version. I could now use their 64-bit version. And you know what? A lot of my over Unity circuits no longer operated anymore. They failed to give me over Unity. Oops. Oh, I liked them so much. They were so much fun. Yeah, because they were so easy that I could really fine-tune them and tweak them exactly the way I wanted to, get exactly the power characteristics I wanted to get within the duration that I wanted to get it. But now I don't get to do that anymore. Now it's tough. Now it's a challenge, but it's still not impossible. And I have sometimes voluntarily tried to induce a challenge because I would get bored, because it was too easy early on in my self-guided tour or study of the topic of free energy. But this was something I didn't plan on. It just happened on its own because I fried my laptop, my old Windows XP laptop that was operating on a 32-bit operating system, and I had to get a new computer. I got it dirt cheap, but it was operating under Windows 10, which just happens to be a 64-bit register, which is exceedingly difficult or nearly impossible, but not impossible, but nearly impossible to get round-off error. So now I can run a simulation, and it's not a fault of the computer giving me false positives anymore. Now it's simply a problem that I have. Can I come up with a circuit that the new 64-bit computer that I'm operating under challenges me to be able to come up with and still get over Unity? And you know what? I can. It's difficult, and it's relatively impossible to regulate the output, but I still can. So what's going on? I'm giving it a microvolt pre-charge condition on a capacitor. That's my favorite way to start up a circuit. Thus, I know that it's over Unity because I ain't giving it energy anymore. It was just a flash in the pan, and not much of a flash at that. 1 microvolt. And I recall from my days of using Paul Falstad's simulator, that's usually in the realm of a little spike in the realm of pico amps, maybe, if I give a microvolt, which means if you multiply a picoamp times a microvolt, it's not a whole lot of watts you're dealing with here. It's probably a femtowatt or something. I don't know. It's or an attowatt. It's something really, really small. You know, e to the negative, let's see, Well, pico is 12, so that would be femto is 15, atto is 18. So e to the negative 15 or e to the negative 18, that's not a whole lot of watts. Yet, it spits out 100,000 watts or more. Usually a lot more. What happened? The circuit's point of view changed its perception of the quantity of energy that it received from the outside world. It altered that perception over a duration of time. Not all at once. Well, sometimes, it would be explosively immediate. That's true. And in fact, in some cases, in Paul Falstad's simulator, I could not get the time frame small enough, the time step small enough to be able to see the explosion happen in slow motion. It was always instantaneous, and that happens in microcap too, in microcap 12 as well. I've had that problem. I can't find out how quickly that boost of energy happened, but it's not a boost. We have to get out of this brainwashing. It's not a boost of energy, even though that's what comes out of the system, out of the power station. The power station is changing its perception of what was given it, what was input. And it's doing so over a period of time, over a duration, due to the manipulation that I program it to do regarding capacitance, inductance, and frequency and phase relation. All that jazz. I play with that over duration, a fifth ingredient, and even though I ignore magnetic reactance, just those 5 factors alone, 1 generic factor of duration and 4 specific factors to electrical reactance specifically, I'm able to get over unity, despite the fact I'm not even dealing with the whole knowledge base on electrical reactance. I'm not using all the ingredients of apple pie that are available to me because I didn't know about them. Now I know about them, and now I should probably start to study them. But regardless of that, this is the relativistic way to explain where free energy comes from and where it disappears into. It's based on how we change our perception of time, of energy that we measure. And admitting that the circuit is doing the same thing. It's changing its perception of energy. Now, I want to finish with one last thought, and it's very important. We go back to duration, the generic factor of time, because let's say that kilowatt hour. Let's now spread it out and diffuse it over a span of 10,000 years. It's still a kilowatt, but now instead of compressed into an hour, it's stretched out over 10,000 years. That's not a whole lot of energy there, but we got to use it, we got to deal with it, we got to adapt. Well, how well do we adapt? Not very well, because it may take a minimum amount of energy to hammer a nail into a board of wood. And if we're dealing with an electric hammer, and it's costing us in kilowatt per hours, but for whatever reason, the electric company cannot deliver us that kilowatt within a span of an hour. Now it has to take 10,000 years to do so. We're not going to be able to hammer that nail because we're not going to be able to overcome the resistance the wood is giving us to pound that nail into the wood all the way, to make it flush, the head of the nail flush with the wood. Because even if we waited 10,000 years for all that energy to be sent, mildly, gingerly tapping that hammer, the head of that nail with our little hammer, with that teeny amount of energy that's been diffused by a factor of 10,000 years by comparison to 1 hour, it won't be enough. You might think, oh no, it should get in there. No, it won't. Because I've seen this happen time and time again within the circuits that I deal with. You are fighting against entropy. It's a race. You're the over-unity engineer trying to engineer over-unity, design it into your circuit. Meanwhile, you're racing against the thermodynamic entropy of the circuit that wants to dissipate energy. You're trying to fill a bucket with water that has holes in it. And you're trying to fill it fast enough so that you keep the water level at the level that you want to keep it at so that your circuit can run. Because if it doesn't have enough water in there, if it just has a drop, your circuit's not going to run. It takes a certain minimum. Well, everybody knows this. It takes a certain amount of energy to run a circuit. And if you got holes in your circuit leaking out energy, wasting it or spending it on friction or whatever, or magnetic leakage, whatever, you've got to make up the difference for all of those losses. And yet you have to do it with a picowatt that you gave it 1 instant, and now it's got to live off that picowatt for the rest of eternities until something wears out, breaks down, and then you got to reboot it after you've swapped out your burnt out parts on another picowatt. But that's not bad. I mean, if your circuit doesn't fry itself in 5 seconds, if it lasts a while, then you don't have to worry about rebooting it with another picowatt until the next time you have to replace parts, or a tree falls on it, and gets in the way of its operation. But regardless of all those extenuating circumstances, we're still living off that picowatt that I pre-charged the capacitor with, because we made more from less per unit time such that it was greater than our thermodynamic, or entropic if you prefer, losses. And plus the energy it took to run the load, not just the losses. So we were able to shift the circuit's perception of energy fast enough within a specific duration such that we can continue to supply it with more energy than it needs to run on, and have a little left over to spare. Hopefully not too much, because we don't want the circuit to fry itself. That's what kind of demand is made upon me when I design an over-unity circuit. I'm racing against time, against the thermodynamics, against the entropy occurring in time at the same time that I want it to manufacture free energy. So it's a race. It's a competition. And it's no wonder that we argue, because that's competition too. Conventional wisdom versus these fantasy buffs who want to think that they can play God and come up with free energy. Well, we can, because it's all about relativity.